In this video, we're to begin to unpack the details of what a linear programming problem is. Now, the title linear programming is a little bit deceptive. There isn't actually any programming per se going on, but this is just what the type of problem is called. So let's build up to this definition, because I think that seeing the definition is not quite indicative of what the aim of this it really is. Now, I like to start with systems of linear equations and then pivot off of that to develop how a linear programming problem is different. So let's say in a systems of linear equations problem, we're crafting two types of bracelets, bracelet A and bracelet B. Maybe we're selling these online. You can make 30 in a day, and you'd like to make $132 in revenue with a day's worth of sales, assuming you sell your daily inventory. So we're assuming that all 30 bracelets are going to sell. You'd like to make $132. You want to make that amount exactly. You're going to make exactly 30 bracelets. If you sell them for $4 and $5 respectively, how many of each should you make? Okay, well, there's the question kind of answers what we're looking for. We're looking for the number of each type of bracelet. I'll define them as X and Y. So the number of, I'll just write this as the number of bracelet A to craft, and Y will be the number of bracelet B to craft. Now we have two constraints. Our constraints are, first of all, remember, constraints are just what limits the values in these variables to a specific pair. So you can make 30 bracelets in a day. We're going to make 30 bracelets, and in these types of problems we assume that that's exactly what you're going to make. You're not going to make fewer or more than that. You're going to make exactly 30. So that means that the sum of the number of A that I craft and the number of B that I craft has to be 30. And the second constraint is we want to make $132 in revenue. $132 in revenue. Now revenue is just what we're going to make in sales. So if we sell 5 of bracelet A at $4 a piece, that'll be 5 times 4 is 20. If we sell 6 of bracelet B, that's going to be 5 times 6 is $30. And then we need to add those together. So we're going to take $4 per bracelet A times the number of bracelet A. That'll give us just the revenue for bracelet A in dollars, plus 5 times X, and we want that to be equal to exactly $132. Now we have different techniques of solving this. One of the ways in which we solve it is we could solve it graphically and find out where these two intersect. And if we look at where this point is, this is the point 1812. So we're going to sell 18 of bracelet A and 12 units of bracelet B for a total of 30. And that'll give us exactly $132 in revenue. The other way we learn how to solve it is to create the augmented matrix and then to row reduce it using Gaussian elimination. And in that case, we would get something that looks like this. We'd get 1, 0, 18, and 0, 1, 12. That's how we would see the solution. Now this is great. This is a great process, but that's assuming that why would we want to make exactly $132 in revenue? Well, in certain situations, we want to maybe hit points exactly, but I think we'd be comfortable with more than that. And I think we could argue that you don't have to make exactly 30 bracelets in a day. You could make fewer, but maybe that's just your capacity. So let's modify the question to reflect that realism. You cannot make more than 30 bracelets, and you would like to maximize your revenue. Okay, well that poses an entirely different question, because now we're saying it doesn't have to be the case that X plus Y equals 30. We can't make more than that. So we could certainly have fewer than 30 bracelets, fewer than 30. But it doesn't say we can't have 30, it just says we can't have more than 30. So that means we can make 30, or we can make fewer than that, right? So X plus Y is going to be somewhere in this interval between 0, 1, 2, all the way up to 30. This is just the set of possible values that these two can add up to. So with that said, let's actually think about this. What would it look like to plot x plus y is less than or equal to 30? Well, it would look like this. It would require us to shade beneath the line. And why do we shade beneath the line? Well, one, because the sum of the variables is less than or equal to 30, and this is a line. So anything below that line will work. Anything that is less than that line. If you pick a point up here, say up here at 32 or 0, 32, well, that's more than 30 bracelets. And similarly, if you go beyond this point right here, well, that's more than 30 of bracelet A, and this would be more than 30 of bracelet B, and here 20 and 20. Well, that wouldn't work, right? Because that's 40 bracelets, so only the region that is underneath. So we could make 10 of it bracelet A and 0 of bracelet B if we pick that point. Or we could make 10 and 10, or we could even make 10 and 20. We could make something in between, like 10 and 18 if we chose to. But what's our objective? Well, we can make up to 30 bracelets, no more than that. And we want to maximize our revenue. Okay, so what we're going to do is we're going to write it like this. We're going to say maximize. Our goal is to maximize our revenue. And how do we get revenue? Well, the way we calculate your revenue, I'll write it as R, and it's going to be 4x plus 5y. It was $4 per one bracelet, bracelet A, and $5 per bracelet B. And here we denoted that we wanted it to be exactly 132. But that doesn't necessarily need to be the case, right? We can make possibly more than that amount. So we're going to write our constraint like this. We're going to write this statement, subject to. That just means we're going to subject it to this limitation. And that limitation is that x plus y must be less than or equal to 30. Okay, so that just denotes that find an ordered pair. So i.e., find an ordered pair in the what we'll call feasible region. Feasible just means possible. The possible region, which is the shaded portion, right? Anywhere that we're allowed, anywhere where the sum of x and y is less than or equal to 30, which is not only underneath the line, but it could also be on the line. It could be on the line x plus y equals 30, right? We can have values along this continuum here, along that line, or below it. So what are we going to do? How are we going to choose this? How are we going to figure out what our maximum revenue is? Well, simply put, it doesn't make a whole lot of sense to pick something, say, down here. I think we can agree on that. Don't pick 0, 0, because although it is the case that you're producing fewer than 30 bracelets, your revenue at that point, let me create a little table here. And what we're going to do is we'll just look at different ordered pairs, and then we'll look at what revenue that ordered pair within the feasible region again just being kind of this triangle. We don't want anything in the negatives. We can't produce negative units, so we're really tied to just this region right here. This is our feasible region. Okay, right there and along here as well. So I didn't do a very good job of highlighting that, but you get the idea. It's going to be anywhere along that line. Let me try a little bit harder. Nope, it's not going to work. It's just not going to work. Okay, there we go. We never give up. So let's look at this point. So we said 0, 0. It's not a good point because 4 times 0 plus 5 times 0 gets you, well, $0 in revenue. And that's definitely not the best point along there. And we said you could pick any point inside of this triangular region or along the edges of it. So I could say, well, let's make 10 of the first unit and 0 of the second, which would be 4 times 10. I get $40 from sales on the first bracelet, but I get $0 in sales in the second bracelet because I'm not making any. So that's better. That's a better outcome, but it's still not the best. And I could do the same thing here. I could say 10. Let's make 10 of each. That's still fewer than 30 units. And 4 times 10 plus 5 times 10 is going to give us $90 in revenue. So you can see we're doing better. Now, where we're ultimately going with this is, well, you're gaining revenue as you produce more and more units. So the idea here is that we would want to max out the number of units we could create. Don't produce fewer than 30. If producing more, at least under the assumptions of this model, if producing more gets you more money, then produce the most that you can. And I think we could say without argument that the most extreme cases would be along the corners of this region. The corners of this region. Because here you're producing to your full potential, 30 and 30. But what about points on the line? How do those compare? Well, let's check the 2 points that we have. So the top one is the point 0, 30. 0 of bracelet A and 30 of bracelet B, which would be 5 times 30. That's $150. You can already see that it doesn't make sense to do that or that or that. But let's also consider the point 30, 0. So we're producing to our max potential. And if I produce 30 of unit A, 4 times 30 is only $120. We're not producing any of unit B. Well, we make more money from bracelet B, so it would make sense that we probably just want to make all bracelet B, right? It doesn't even make sense to make a few bracelet A if bracelet B is going to yield you the most money, and you can ensure that you'll be able to sell all of them out. It would just make the most sense to produce all of bracelet B. So under that intuitive guideline, we don't want to pick something like this, 10, 20. And let's think about why not. Well, here you're producing, as opposed to this starred ordered pair where you're making more of your bigger money producer. You're producing 30 units at $5 a unit. But here now you're mixing a combination of them. You're saying, well, I'm going to make $4 a unit for these 10 units, which that will give me $40. But then I'm going to only produce 20 of the $5 per unit producing product. 20 times 5 is 100. Then you can see that falls short of our potential here because we can make an extra $10 by shifting all of our bracelet A into our bracelet B. So our optimal solution here is to produce 0 of A and 30 of B to maximize our revenue at $150. You can see that that's better than what we did up here. Here we were able to achieve exactly $132, but that was because we wanted that exact revenue and we wanted to produce exactly 30 units. Here we said you can't produce more than 30 units, you can produce fewer, but figure out how many of each you should manufacture to make your revenue as large as possible. So the revenue is the unknown here, and what is known as that we can pick any ordered pair in this shaded region. So this is a linear programming problem. You can see that our constraints are, well, you can't max out, you can't go beyond this point, but try to find a point that will give you the biggest possible, in this case, revenue. And this is kind of the general basis of linear programming problems. An linear programming problem, sometimes we abbreviate that as an LP, linear programming problem, is one in which our constraints are inequalities. And inequality just means that not equal to or not necessarily equal to. We only study greater than or equal to and less than or equal to. We don't study greater than and less than. Why not? Well, because then that would exclude points on the line, and then that makes things a little bit more complicated because now how close can we get to the line without touching the line, and that starts to be a trickier business than we're allowing. So we're only focusing on Not strict inequalities, but inequalities that are greater than or equal to, less than or equal to. And the goal is to maximize, which is what we did here, revenue, or minimize, in some cases, maybe we want to minimize cost, and we call that quantity that we want to maximize or minimize our objective function. So our objective function was the thing that we wanted to maximize, which we just denoted as r equals 4x plus 5y. This was our objective function. It's a function because this is what we were plugging our ordered pairs into, and the output would give us the revenue, and our objective is to make the output of this as large as possible while sticking to our constraints.